All right, last time we did O3, where we had our 3x3. We had our 2 bonding, we had our non-bonding, and we had our 2 anti-bonding. So we had pi1. Right. Okay, we had pi1, we had pi2, which was overall 0 bonding. So it is then an N for non-bonding. And then pi star 3 was 2 antibonds. All right, so when we had our structure here and we had our 2 resonance forms, when you draw the 2 resonance forms, the 2 electrons come in to make a pi bond, and these 2 electrons from the pi bond go out to that oxygen, and you have your double bond on the other side. All right, so you have your plus oxygen still here, but now you've got your neutral oxygen on the right, and now your negative oxygen is on the left. All right, and so when we put in our pi bonds, all right, so when you have electrons making a pi bond, those are pi electrons. When you have electrons coming out of a pi bond, those are also pi electrons. So O3 has 4 pi electrons. And so when we put in our electrons, we had to put in 4, not 2 electrons, but 4. And so this is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital. And again, if this is on the test, it will be extra credit. I wouldn't spend a lot of time on that. But what is most likely going to be on the test is covalent radii. Hopefully there were homework problems with covalent radii on them. They're very simple, but just because they're simple, if you haven't seen them, you won't know what to do. All right, so covalent radii, there's a chart in the book. So it'll say that the covalent radii of chlorine is 0.99 angstroms. All right, so this comes from a chart. All right, so you're going to be given the covalent radii chart. And so then the question is going to be, calculate the Cl-Cl bond distance. All right, and so again, all you have to do is know that you have your Cl, all right, and it's got a radius, and then you have another Cl, and it has its radius. And so the bond length is simply the radius of this chlorine plus the radius of this chlorine. So it's simply 0.99 angstroms plus 0.99 angstroms. And so it's 1.98 angstroms. So it is as simple as that. You simply add up the 2 radii that are given on table 9.4, I think it is. But that table is going to be given on the test. And you simply add the 2 radiuses together of whatever 2 atoms are connecting together. And you simply add those up to get the bond length. If they gave you the bond length of a Cl2, all right, then they could ask for what is the radius. Well, then you simply divide it by 2. So you can work that in reverse. Now, the only time you can do that in reverse is it has to be the same atom. Because if they gave you the length of, HCl and said, what's the covalent radius of Cl, you can't do that because H and Cl will have different radiuses. But yes, so anyway, the chart is very simple. You just add up the 2 radiuses. That gives you the bond length. All right, so we're going to go through the chapter 5 practice, which is on this chart here. All right, so in number 1, and this again is going to be most of the test, it says to give the geometric arrangement. GA is geometric arrangement. That's you get from the number of directions, bonding directions plus your lone pair directions. And then that will correspond to the hybridization, the hybrid orbital, whether it's SP, SP2, SP3, SP3D, SP3D2. Then draw the molecule in 3 dimensions. You have to know how to draw a tetrahedral, a trigonal bipyramidal, an octahedral. Then the molecular geometry, remember the electron pairs are invisible, so you then have to know what that shape is called. Then give the bond angles. Then you have to show the bond dipoles pointing to the more electronegative atom. Then the molecular dipole, that is for the center of plus, center of minus. And note that we have A through N here because this is, again, this is about half of your test. Of the 150 points, this is 75 of the points. All right, so let's start with PF5. And let's do all of these things for PF5. All right, so you go to the periodic table, you find P, it is in column number 5. This has 5 valence electrons. Then you find F, it has 7 valence electrons on your periodic table. We have 5 of them. All right, and so then you add these up. So 5 and then 7 times 5 is 35, so that's 40 valence electrons. All right, so that is the total valence electrons. The first atom listed is the central atom, unless it's H. H is never a central atom. All right, and so you have your P, and then you put around your 5 Fs. All right, and every bond has 2 electrons, and so we put in 10 electrons. So we're going to subtract 10 electrons, and we have 30 electrons remaining. And then we're going to try to give every F an octet to see if 30 is enough. You have 30 after you're going to put octet around each of these fluorines. So each fluorine has to have 6 electrons because it has the bond for 2, and then it needs 6 more electrons. And so 6 times 5 is exactly 30. And so that's the exact number that we needed for everything to have an octet. So once you have that, this is your Lewis structure. All right, so you base all of your answers off of the Lewis structure. So how many directions do we have? 5. So there are 5 directions. So that gives us our geometric arrangement. Anytime we have 5 directions, that is going to be called what? Trigonal Bipyramidal. All right, and so since we have 5 directions, we need 5 orbitals to hybridize. And so what is the 5 hybrid orbitals? D. So S is 1, then 3 of the P's, that's 4, and then a D, that's 5 orbitals that hybridize into degenerate orbitals, same energy orbitals. All right, now since all of our directions were bonding directions, then our molecular geometry, well, next is 3 dimensions. So now you have to be able to draw a trigonal bipyramidal in 3 dimensions. All right, and so you have to know that you're going to have your P, you're going to have your axial positions up and down, and then you're going to have your equatorial positions, where that's going back, that's coming out, and that one is in the plane. All right, and so this is how you draw your trigonal bipyramidal. All right, and so since there are no electron pairs, nothing that is invisible, when you have no electron pairs, then your geometric arrangement and your molecular geometry are exactly the same. All right, so then you have your bond angles. So you have your 90 degrees, you have your 180 degrees, and your equatorial ones are 120s because they make a trigonal planar in the middle. And so you have your 90, your 120, and your 180 bond angles. When you're showing your bond dipoles, the most electronegative element is fluorine, and so you are going to draw the electrons moving towards your fluorine, the more electronegative, and each fluorine will have delta minus. And so your P has the delta plus. And so those are your 5 bonds. Those are your 5 bond dipoles. Then when you do the molecular geometry, so the center of delta plus is at P. Now we look at the center of delta minus. So the center of delta minus is at P, completely surrounding the P. Center of delta minus also at P. Okay, so you have a minus up and down, so the center of that is right in the middle of it, right on the P. And then you are surrounding the middle with negatives. So the center of that is the center of that circle, which is at the P. So it is exactly what it is. It's where is the center of that negative charge. And when they are at the same place, then it is a non-polar molecule. All right, and so this has a dipole moment of 0. So if you're nonpolar, then your dipole moment is 0. The next one is BRF3. All right, so BR is in the same column as F, and so they're all 7s. We have 7 for the BR, and we have 7 times 3, which is 21 for the 3 Fs. All right, so the total is 21 plus 7. That is 28 valence electrons. All right, we did not... the reason why there are no formal charges up here when we did our PF5 is fluorine was supposed to bring in 7, and each one of these fluorines brought in 7, and so there is no charge for the fluorines. The phosphorus was supposed to bring in 5. The phosphorus brought in 5 electrons, and so that is why phosphorus is also neutral. All right, so now we have our BRF3. So our central atom is Br. And then we have an F, we have an F, and we have an F. So we subtract 6 for the 3 sigma bonds. The single bonds, every bond is 2 electrons. We have 22 electrons. And so when we put in an octet, 1, 2, 3, 4, 5, 6 for each of these fluorines, all right, so that's 18. And then we need 2 for the bromine. We need 20. We have 2 extra. All right, so everything has an octet, but we have 2 extra electrons. When you have extra electrons, they go on the central atom. And so those extra electrons are going to go on the central atom. If you don't have enough electrons, then we're going to add a pi bond. If you have too many electrons, they go to the central atom. All right, so now you have your Lewis structure. Here is your Lewis structure. You have 3 bonding directions, and you have 2 lone pair directions. So you have a total of 5 directions. And when you have 5 directions, your geometric arrangement is trigonal bipyramidal. When you have 5 directions, you need 5 orbitals to be hybridized. So that's an S, all 3 of the P's, and 1 of the D orbitals. So it's sp3d for your hybrid orbital. All right, so then again, we have to draw it in 3 dimensions. So when we draw this one in 3 dimensions, you have your 2 axial positions and you have your 3 equatorial positions. But you have to know that the electrons, the lone pairs of electrons, must go in the equatorial positions. So the electrons must go in the equatorial positions. All right, and then the 3 fluorines, first 2 are going to go into the axial position, and then the third one will go into an equatorial position. All right, so lone pairs always go in the equatorial positions. The axial positions will be where your first couple of atoms will go, and then the rest of them will then go equatorial. All right, so that is drawing it in 3 dimensions. Now you see the molecular geometry is different. Anytime you have lone pairs on the central atom, your geometric arrangement and your molecular geometry will be different. All right, and so this one is simply called T-shaped. So the electron pairs are invisible, and so this just makes a T. And so it is T-shaped. And now your bond angle. So the bond angle is, a lone pair is not a bond. All right, so the bond angles, we have our 90 and our 180, but we don't have 120. This is not a bond. So these are simply 90 and 180 degrees. So we still have the 180, we still have the 90. We do not have any of our 120s that are the equatorial positions. All right, so then we do our bond dipoles. And so when you have fluorine, you know that fluorine is the most electronegative atom. And so all of the fluorines are delta minus. Now your electron pairs are right on the bromine, but they will pull out a little bit of electrons, but again, they are right next to the bromine, so they are right there. All right, so the bromine is delta plus. So now we have to find the center of delta minus. So you have a top and a minus, a top and a bottom for the delta minus, so that would be right on the bromine. But over here, we have a delta minus way out to the right, and these delta minuses are right next to the bromine. And so your center of delta minus is going to be right in here somewhere. You don't have to be real accurate with it, but it's between the bromine and the fluorine. So your center of delta minus is here. Your center of delta plus is here. All right, so I'm just bringing it down. So here's where your bromine's at. Center of delta plus. I erased all my delta minuses. Okay. All right, and center of delta plus is right there. So your center of delta plus is right on the bromine. The center of delta minus is between the Br and the F. All right, and so your molecular dipole is going to the right, as drawn in this picture. And so all you can say is that it is a polar molecule. It has a difference in the position of the center of delta plus and the center of delta minus. So this is a polar molecule. In order to be nonpolar, it has to be completely symmetrical, exactly the same all around it. All right, next one is BRF5. Yep. Okay. So that you can never go over 8 for row 2. So you're talking about lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. These can never have more than 8 because, and then well, hydrogen can never have more than 2. All right, because hydrogen has the 1s2. That's it. 2. 1 bond for hydrogen. If there's anything else, it's wrong. When you get to row 2, you have the 2s2 and the 2p6. All right, so you have a maximum of 8. If you have more than 8, then it is going to be a violation. And also true about this row is that your nitrogen, oxygen, fluorine are strongly electronegative, and they must have an octet. All right, so these never have an octet, pretty much never, but rarely have an octet, usually less than 8. And carbon here normally has 8. All right, so you have the NOF always have 8 electrons. every single structure you have that has a nitrogen, an oxygen, or a fluorine in it, it is going to have 8, exactly 8, and no other number. Carbon, all neutral carbons have 8, all negative carbons have 8. If you have a carbocation, a positive carbon, that will have less than 8, it will have 6, and that is okay. You can have less than the max, but you can't have more than the max. All right, but boron normally has 6, not 8. And beryllium normally has 4, not 8. And lithium usually has 2, not 8. So you can have less than 8, and that is fine. 8 is the best, but 8 is required for nitrogen, oxygen, and fluorine. But once you get below that, then you go to 3. So once you're down at the 3, then you have the 3s2, you have the 3p6, and you have the 3d10. So now you have a maximum of 18. And so you can't ever put too many, pretty much. I mean, I've never seen one with 9 bonds to it. So it's very difficult to violate the 18 electron rule and put more than 18 on that. So when you have your bromine here, and you see you have 2, 4, 6, 8, 10 electrons, that's fine because you have fluorine, bromine. Actually, bromine actually has the 4F14. It could have 32 electrons if it wouldn't violate any rules. The reason why this bromine is neutral, because it's supposed to bring in 7. Note that it brought in 1, 2, 3, 4 lone pairs, then 5 to share with this one, and 6 to share with this one, and 7 to share with that one. So bromine was supposed to bring in 7, and it did, and then it's neutral. But yeah, the only ones that must have an octet are nitrogen, oxygen, fluorine. Those are the ones that must have an octet. Carbon almost always has an octet, but it can have less than 8. But again, once you get down below, you can have pretty much as many electrons as you want. But the most stable is still going to be 8, even for the ones that are below. All right, so again, you have 7, and then you have 5 times 7. So this time you have 42 valence electrons. And the central atom is Br, and that's bonded to 5 Fs. All right, and then a Lewis structure doesn't show anything. Like I put all 5 of these bonds to the right. It doesn't matter where you put the 5 bonds. All right, and so a Lewis structure just puts in the electrons. So we put in 5 bonds. So we subtract 10 electrons. That's our 5 sigma bonds. And that's fine because bromine, if the F was the central atom, you couldn't put 5 bonds on it. But bromine, you can. All right, so 32. But what we need is just 30 again. We have, again, our 6 electrons for the 5 fluorines. We only need 30 electrons to give all these fluorines that must have an octet. So again, we have 2 extra. And again, when you have extra electrons, they go on the central atom. All right, so then you have to do the number of directions. And so you have your 5 bonds. And you have your 1 lone pair. So you have your 6 directions. And so that tells you that the geometric arrangement has to be octahedral. And your hybrid orbital, you have 6 directions. You have to have 6 orbitals. You have the s orbital. You have 3 of the p orbitals. And now you need 2 of the d orbitals. 1 s, 3 p's, 2 d's. That is 6 orbitals that hybridize to give your sp3d2. All right, so then you have to draw it in 3 dimensions. And so now you have to be able to draw an octahedral. You have straight up, straight down, and then you have a square planar in the middle where 2 are going back and 2 are coming out. All right, and with your octahedral, every one of these spots is exactly the same. It doesn't matter where you put the electron pair. When I'm doing an octahedral, my first pair always goes on bottom. Again, it doesn't matter where you put it. It's all the same. If you see well in 3 dimensions, you will see that all of those are the same. All right, so you put your fluorine, your fluorine, your fluorine, your fluorine, and your fluorine. You put in your electron pairs. And there is your 3-dimensional picture of your BRF5. And so now you got to find out what this molecular geometry is called. Again, you cannot see, there's no nucleus for an electron pair, so you don't see that. So the molecular geometry is square on the bottom going up to this F. So that is a square pyramidal. And then the bond angle, 90 and 180. All right, so then when you're doing the bond dipoles, again, we like it when we have an F because we know that there is nothing more electronegative than an F. And so we point to all of the F's. Every F is delta minus. And then, so your bromine is delta plus. And remember, your electron pair is right next to the bromine, so you could draw a tiny little arrow. All right, so you could draw a tiny little arrow. The electrons are coming out a little bit, but the electron pair is right on the bromine. There's not a bond distance away from the bromine. All right, and so your center of delta plus is right on the bromine. So that's where my center of delta plus is, right on top of the bromine as I come over here. All right, so the square planar in the middle, they all cancel each other out. This negative, this negative, this negative, this negative, all centered on the bromine. All right, so now the bromine has the negative and this fluorine. And so now we see that up above, we're going to have our center of delta minus above the bromine. And so the center of delta minus is right there. And so our molecular dipole is here, from the center of plus to the center of minus. And so this is polar. This molecule is polar. All right, SCl4 is the next one. All right, so sulfur is in the same column as oxygen. That is in column number 6. Fluorine, again, is the halogens where they have 7 valence electrons. And so we have 34. We add up our 6 plus our 7 times 4. You get 34 valence electrons. And so S is the first atom that's not a hydrogen. That is your central atom. It's bonded to 4 fluorines. All right, and so we subtract 8. We have 26. We only need 24. Again, we have 2 extra. Anytime you have extra electrons, they go on the central atom. All right, and so we do our bonds. There are 4 bonding directions, and there's 1 lone pair on our central atom. And so we have 5 directions on the central atom. All right, so again, when we have 5 directions, your geometric arrangement, trigonal bipyramidal, hybrid orbital, sp3d. All right, so now we have to draw in 3 dimensions. And so the 5 direction is a trigonal bipyramidal. You have to remember that your electron pair has to go in the equatorial position. I don't care if it's this one, or this one. It cannot be in axial position. And so your fluorines go here, 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 and here. And so here is your 3-dimensional structure. All right, and so you need to now have the molecular geometry. So if you see this, here's the 2 legs, and here is the person sitting on this side and the person sitting on that side. And this is a seesaw. So the name of that is a seesaw. If you put the electron pair at the bottom, it would be a trigonal pyramidal. Trigonal pyramidal is not the shape. This is a seesaw. All right, bond angle. So this time we have the 90. We also have the 180, and we now still have our 120. So we have all 3, the 90, the 120, and the 180. 90 from axial to equatorial. Between the 2 equatorials is 120, and axial top to axial bottom is 180-degree bonding. All right. Then you do your bond dipoles. Again, F, most electronegative atom. So the electrons are moving towards the F in all of these bonds. So delta minus for each one of these Fs. And so again, electron pair is right on the sulfur. It has a very tiny arrow. It is not a bond distance. It is right next to the S. So the center of delta plus is right here on the S. So the center of delta plus is right there on the S. So the top and the bottom delta minus, that comes right to the S. The ones that are going back and coming out, the center of delta minus is, well, right here. So we have a delta minus here and here. So the center of that delta minus is right in between the S and the F to the left. So the center of delta minus is there. And so we have our molecular dipole. So this is a polar molecule. So it is not equal to 0. The dipole moment is not equal to 0. Anytime you have one lone pair, it is going to be polar 100% of the time. If you have more than one lone pair, it may or may not be polar. If there are no lone pairs on the central atom and you have the same atom surrounding it, then you will be a nonpolar molecule. It will be completely symmetrical. All right. SEF2. All right, so Se is right below sulfur on the periodic table. So that is 6 valence electrons. And then we have 7 times 2. So we have a total of 20 valence electrons. Se is the central atom. And so it is bonded to 2 Fs. So the bonds require 2 electrons. And so 2 bonds require 4. We have 16 electrons. Which is the perfect number to give all of the atoms an octet. All right, so there is our Lewis structure. All right, so we look at our central atoms. We have 2 bonds, and we have 2 lone pairs. We have 4 directions on our central atom. All right, and so now we can get our geometric arrangement. 4 directions we know is tetrahedral. And we know that the 4 directions require 4 orbitals, the s orbital and all 3 of the p's for an sp3 hybrid orbital. All right, so then we have to draw it in 3 dimensions. You have to be able to draw a tetrahedral. And so a tetrahedral has 2 in the plane, 1 going back and 1 going out. And it doesn't make any difference where you put the 2 Fs and the 2 lone pairs. It makes 0 difference. You can put these 2 lone pairs anywhere you want. I picked the going back and the coming out positions, but it doesn't matter. And so your molecular geometry, what does it look like? Well, it looks like it is bent. And then the bond angle. All right, so bent has 2 different bond angles. The bent could be 109.5 and the bent could be 120. When you are tetrahedral, your bond angles are 109.5. If you were trigonal planar, then your bond angle would be 120. All right, so this is a tetrahedral, the bond angle 109.5. Most likely this is going to be less than 109.5, but I'm just looking at the predicted bond angle of 109.5. All right, and so then again, we got fluorines. We like it when we have fluorine because we know that's the most electronegative atom, and so that's going to be your delta minuses. Se is going to have the delta plus. Remember, your lone pairs are right next to the Se. They are pulling out, but they're right next to them. All right, and so the center of delta minus is right here. between these two F's. Here's your center of delta minus. This is the only delta plus, so that is then the center of delta plus. And so your molecular dipole is right here. And so this is a polar molecule. NCl3. All right, so nitrogen is in the 5th column, so it has 5 valence electrons. Chlorine is a halogen, 7 valence electrons, times 3 is 21, plus 5 is 26 valence electrons. Central atom is N, bonded to 3 Cl's. So we subtract 6, because every bond is 2 electrons. And so we have 20 valence electrons, and that is the perfect number to give all of the atoms an octet. Again, if we don't have enough, we have to put in a pi bond. If we have too many, we put them on the central atom. This one had the perfect number, and so we get the number of directions. We have 3 bonds, and we have 1 lone pair. So we have 4 directions. All right, so your geometric arrangement is tetrahedral. Your hybridization for tetrahedral, always sp3. You have 4 directions. It's always tetrahedral sp3 every time you have 4 directions. Now you have to draw it in 3 dimensions in order to see what is the molecular geometry. Tetrahedral, every position is exactly the same. It doesn't matter where you put the electron pair. I will put it on the top. And that's bonded to Cl, Cl, Cl. And so this is your 3-dimensional picture. All right, and so your electron pair is invisible, so you have your triangle base coming up to an N. This is a trigonal pyramidal. And the bond angle for tetrahedral, 109.5. All right, and then chlorine is one that we have memorized. The electronegativity of chlorine is 3.2. The electronegativity of nitrogen is 3.0. And so we are drawing our arrow to the higher number, which is the chlorine. All right, and so we have our delta minus, delta minus, delta minus at the chlorines, delta plus at the nitrogen. Again, this electron pair is right next to the nitrogen. And so your center of delta minus is right below your nitrogen. The center of delta plus is right on top of the nitrogen. And so you have your molecular dipole that goes down in this picture. And so this is a polar molecule. Again, we have 1 electron pair. Anytime you have 1 electron pair, you're going to be polar. It is not going to be perfectly symmetrical. It's impossible to be perfectly symmetrical when you have 1 lone pair of electrons. All right, so you should work on these problems, see if you can get them right, and then we are going to do them tomorrow.